Okay, so we'll wait for a few more minutes to see if anyone else is joining, and then we'll start. So, hello everyone. Good evening. Welcome to this live interaction session of this particular NPTEL course named as Waste to Energy Conversion. So, my name is Devadun Banerjee. I'm going to share my screen here. So, welcome. My name is Devadun Banerjee. I'm a PhD PMRF scholar from Indian Institute of Technology, Delhi. We're going to discuss about a bit of this NPTEL course, Waste to Energy Conversion. It will be mostly focused on the week one content. So, and we will also try to discuss some of the sample problems which will help you to solve your assignments and might be helpful for your exam later on. So, in this week, the first two lectures covered majorly the overview or the introduction part of this waste to energy conversion technologies. It covered mainly the definition of wastes, their classification, the various important quality parameters of different types of wastes, and the different types of wastes like solid waste or wastewater, or what kind of wastes are actually suitable for energy production. And then the other types, majorly in solid waste. When we talk about solid waste, it might be agro waste, it might be forest, it might be industrial waste or municipal solid waste. So which are those, the availability, and the what are the data currently available in India, and the different routes of solid waste management and needs of energy production from waste in and different scenarios and like that. First two lectures covered these contents. So if we go to the lectures, so the lecture starts with the basic definition of the wastes and their classification. So what are wastes? Wastes are basically those materials which are not the prime products for a producer. So basically a simple thing, we know what is waste. I don't know. I don't think it's very crucial to make much comment on it. Waste is nothing but something a byproduct. When you're trying to produce something, there is something unwanted thing which we accidentally produce or we concurrently produce. So that is called as a waste, and which is required to be discarded or recovered. So we can actually classify waste based on different bases. Uh, it can be classified based on its hazardous nature. So based on this, we can term it as hazardous waste or non-hazardous waste. And based on its phase, whether it's solid, whether it's liquid, or it's gaseous, it can also be classified. And when you talk about the hazardous waste and non-hazardous waste, so why these particular things are important? Because the hazardous waste poses a certain amount of threats to our society or our health. And so therefore its toxicity, its reactivity, its corrosivity, and its ignitability, these kind of factors become much more prominent, and that is why it needs to be segregated in this part by this kind of basis, whether it's hazardous nature or it's non-hazardous, and based on that its handling and processing would be uh, depicted. So as I told that should be certain parameters, certain factors based on which the waste can be segregated or categorized. Based on that, what can be the important quality parameters? The important quality parameters are the message. Am I not audible?
Audible to me.
Okay. Yeah, and someone asked, sir, can we access the class recordings? Yes, you can. I think there is one link that is shared with you, or it would be shared. There is a log sheet which contains the YouTube link. So these kind of lectures are usually uploaded in YouTube. So you'll just go to YouTube to the link, and then you can just access these recordings even after for like permanently. They will be there. Okay. Okay. So I want to know before going forward, like, have you guys watched the NPTEL first week lectures or have gone through the things, because that would be much more easier to comprehend, I think. And if not, then it would be good. So uh, go through the lectures, go through the videos. So that would be a good thing along with that. Okay. So coming back to our discussion. So the solid waste can be basically different quality parameters include the elemental composition, its proximate analysis results like moisture content, volatile matter, and ash content, its bulk density, its heating value, very important, especially for the waste to energy conversion point of view, its permeability or hydraulic conductivity, its particle size distribution. These are the main quality parameters of solid waste. Similarly, for wastewater is biological oxygen demand, chemical oxygen demand, total organic carbon, pH, total dissolved solid, total suspended solid, TDS, TSS, color and odor, cations and anions, like that. Similarly, in the gaseous waste, its particulate matter, its NOx, SOx, carbon monoxide, heavy metals, and other different materials like hydrocarbons or other fuel molecules or other gas components. So, as I initially also told that what kind of wastes actually suitable for energy production. So, it can be actually answered via these quality parameters. So, waste which can be used is it should have a high carbon content, it should have a high heating value. Similarly, wastewater with high biological oxygen demand and chemical oxygen demand value. And similarly, waste gases with high heating value. So this kind of important parameter uh, emphasized. And this particular course is concentrated on solid wastes basically and wastewater a bit. I would be more focused on the solid wastes, yeah, and also to some extent the wastewater also. So compared in the solid waste classification, if we go, so I'll be discussing it further. Like bit can be discussed upon the based classified based on the source, based on biodegradability, based on combustibility, compostability, and usability. So these are the basic classification of the solid wastes. Similarly, there are like say about mainly the 50% solid waste are biodegradable in nature, 20% are recyclable, and 22% are inerts. So you can find this kind of what comes under which category. So these are some datas like different the composition and heating values of solid waste in different cities and all different regions. So not going into much detail. So if we call the other part of the solid waste is the agricultural waste. So in agricultural waste, it the agricultural crop is usually lignocellulosic or
We can't see the slides.
non-lignocellulosic.
Sorry, can't see the slides. I don't know. Is it for others or only for me?
Okay, okay. I'll just again unshare and share. Is it visible now?
Yes, yeah, thank you.
So, so the non-lignocellulosic biomass is basically edible in nature, and that is why for fuel production, for energy production nowadays, the lignocellulosic biomass or lignocellulosic agricultural waste are being focused upon. So it contains majorly cellulose, hemicellulose, lignin as major components. Based on their relative compositions, they are further like the difference is made, and based on that, the difference in their heating value and difference in their the energy production, those kind of things happen. Similarly, wastewater. has also their different classification. Like wastewater can be obtained from the oil spilling, the rain leachate, from industries, from domestics, from seawater, or some storm drains. So these kind of different sources can be there for wastewater. So a very typical composition of untreated domestic wastewater are shown here. So based on the already told this kind of quality parameters like the total solids, total dissolved solid, total suspended solid, BOD, COD. Based on that, these are made of different classes like low strength, medium strength, high strength, like that. Okay. Basically, in this case, the BOD and COD, that is the most important quality parameters of a particular wastewater. So basically, if we there's a simple relationship like that, higher BOD and higher COD, it means its concentration is more and more strong, and that is why it's based on that. The It's low strength, having a low BOD of about 110, or in the COD 250. Similarly, medium strength having about double. So it's a kind of a typical composition. Obviously, it's not a constant value. It would be depending on the various factors and the sources. Similarly, different types of other like wastewater's composition, like depending on the sources, pulp and paper industry source, distillery source, sugar industry, all those things are classified, and the loads of these data are available in your note sheet. So the and again the further availability of the agro waste, forest, industrial, municipal solid waste in India, those data are presented in this particular lecture. So based on that, you can see that the generation of municipal solid waste is expected to rise by roughly about 8% per year. So as we call that nowadays, the climate change and waste management, these are the most two prominent problems in global scenario as well as from an Indian scenario. So, however, this data is not very recent. Like in 2011 report, about close to 2 billion tons of municipal solid waste are generated around the world. So obviously, this particular values is also is increased. That is why called as roughly about 8 to 10% increase is usually exhibited. So, so when you talk about the solid waste management, so there are different routes for the solid waste management. So usually the at source it is segregated. So that is why that the initial classification is very important. Whether it's a recyclable, whether it's a hazardous, whether it's a inert, or whether it's a non-hazardous organic kind of fraction. So after that segregation, the recyclable waste can be further segregated into combustible and non-combustible. So the combustible parts basically goes for the fuel production and also some in the packing material or paper uh, formation. Or the non-combustible parts such as the metals, glasses, those kind of materials are comes under the non-combustible, and those goes to the recycling industries. So this kind of glass and metals can be recycled, can be recovered from the waste, and then again goes back to the sources to synthesize further items. So these form the part of the circular economy. Similarly, the combustible goes for the fuel production. So uh, that comes majorly in the waste to energy conversion thing. Similarly, the organic fraction, it undergoes a biological treatment. What comes under biological treatment? The composting, vermicomposting, biogas, landfill gas, like this. So for this preparation, this kind of via these biological treatments, this kind of organic wastes are treated. And similarly, other like inert and hazardous waste are also treated. Not going to much detail for that. And further, some data are also shared. to with in the first lecture. Now we come to the second lecture. So after the routes of for solid waste management is covered in the first lecture. Now the second one, need of energy production from wastes. So these are interesting things like uh, why do we want to produce energy from waste? There are some points mentioned here: need of sustainable development, increasing generation of wastes and power demand, energy potential of some solid waste components and wastewaters, reduction of inert in municipal solid waste. So, uh, as I told, the climate change and the waste management are the most two prominent problems globally nowadays. So, to tackle these two challenges together, this particular thing of waste conversion to energy or waste conversion to value added products are the most important solution. So, uh, until and unless we reduce the amount of waste lying and the waste composted or incinerated, we cannot tackle the climate change as well as the growing energy demand as well. So there is a high amount of energy demand with the growing population and with the growing, development, the modernization of the current global, right? So with to tackle this kind of situations, this particular conversion of this waste to a high energy material or particular direct energy production is important. And obviously, as can be as is written here, like some of the solid waste components having a high energy value or high heating value or high energy potential. So why do we waste that particular energy potential? So ultimately, if we do a kind of like techno-economic analysis or life cycle analysis, then you would find that it is becoming a much more uh, economically viable and environmentally benign if we convert this particular solid waste components or the wastewaters to some energy material or directly produce some energy from it. So as I told that the environment, economic and the social. So at the conjunction of all these three, it comes the sustainable development. So it have the economic part, it has the environmental impact, environmental viability, environmental positive approach, and the social responsibility. So that is why the energy production from waste are very very important. Uh, so why this again the solid waste management, proper solid waste managements are important. So if we don't do the proper solid waste management, what would cause is it would cause air pollution, water pollution, soil pollution, the different types of pollution basically. Again, the environmental contamination is so during the process. Obviously, no process is absolutely emission free or absolutely 100% green. So during the process, obviously there is some pollution, there is some contamination in some way or the other. Now, if we also make some waste and then we don't treat it properly, again that particular waste would also cause some other form of the pollutions like air pollution, water pollution, soil pollution, like that. So what are the some examples? Like the municipal solid waste clogs the drainage system. Right, we have seen this, like the plastics and all those kind of solid waste, which are not very much biodegradable. They actually block your drainage system, pipe, the sewage things, and ultimately it causes a the stagnant water, then it causes some breeding of some mosquitoes or insects or like that things. And then obviously your, if your wastewater pipe is getting clogged, then it would ultimately overflow and it causes the floods and all these things. So uh, togetherly all kinds of pollution, all kinds of environmental contamination, it takes part in. And then again, we talked about the water pollution, soil pollution, like that, land pollution. But how air pollution is operating is because if we do some direct incineration or landfilling, so what would cause is, it would cause some greenhouse gases emission, like carbon monoxide, carbon dioxide, methane, like those kind of greenhouse gases. So, so ultimately, these greenhouse gases would get emitted into the atmosphere, and because of the atmospheric emission of the greenhouse gases by via the decomposition of the organic wastes, the air pollution would occur. And ultimately we have as already told, that we have certain social responsibility. So in terms of the social thing, the public health, it's also something which needs to be monitored. And that is why, like, hazardous and non-hazardous kind of wastes are should be segregated. So otherwise what would happen is, there would cause some health problem, such as the nose and throat infection, breathing infection, bacterial infection, like that. And based on that, the energy production for basically again, the as I told, that the increasing amount of waste with the globalization, with the modernization of our society nowadays, one example of this increasing amount of waste is actually shown here. But compared to the last about 25, 26 years, it can be seen that per day is about there was about, if we see about the middle income countries such as India, there's about zero point 0.5 to 1.1 kg per day municipal solid waste is generated, which is a very very big amount at that time. But nowadays there is about 1.5 times increase already in this last 25 years, right? So that is why it's more and more focus towards choosing these kind of sources for energy production, for other value added chemicals production. Those are very very important. And again, further some of the data are provided for different cities in India. And if we see this the ratio of basically the different different types of the waste materials, so you can see that the basically the inert materials is actually getting decreased, and comparatively the compostable has having a much higher increase, and also the recyclables are having a also steady increase. So it means that the some in some way or the other, the municipal solid waste to energy conversion, these kind of things are getting more and more encouraged. And one such example is that the reduction of the inert materials in the municipal solid waste. And some further examples are shown here. And and if we want to say an overview and overall scenario of this particular waste to energy conversion is, we can tell that the waste to energy technologies use municipal solid waste or any other waste material containing huge amounts of renewable and biological materials to generate heat, electricity and fuel through different complex conversion methods. This is a kind of a one line statement about this overall scenario. What is a waste to energy? technology conversion. The considerable amount of municipal solid waste around the world has given the waste to energy technologies a new lease of life and the much needed impetus. Several environmentalists and other players are working towards for commercializing these waste materials into a viable fuel source. I've already talked about this. So this kind of thing, like the cycle of the waste to energy, is also very much important. So, and in a household, there is certain amount of wastes are generated. Then these are thermally treated in the waste to energy plants, and then to from the plants we get the different the energy sources, the fuels in different forms, whether it's a liquid fuel, whether it's a solid fuel, or some other. And from that particular waste to energy conversion, there is certain amount of heat is also provided. That heat we can further utilize for the inhabitants, the households, or some other utilizing that particular heat, some other industries or some other roadside electricity, street lights, all those things can also be used. It can be used to generate the electricity. Again, those electricity, that particular directly, that electricity can be used to supply the households and the society. So ultimately, you're saving and saving. So it basically works in kind of this kind of waste to energy cycle in a cyclic form, which is ultimately the target towards a circular economy rather than a linear economy. Okay. And some other not going to this kind of details of these particular datas, can easily find them. So lot and lot of focus is nowadays is being put on the renewable energies such as the wind energy, hydropower, biomass, and among that the waste to energy also. So still, if you see, again this data is not very recent, it's 2014 data, but still you can see that only 2% that particular the waste to energy part is there among the total renewable powered sources, with the majority is captured via the wind power energy. So that is the target to increase this particular waste to energy sector, waste to energy segment uh, further. Okay. So and then this kind of some Indian data and Indian information, where basically the main institutions which govern or which determine the energy policy of the country, those are listed here, such as the Ministry of External Affairs, Ministry of Environment, Forest, Climate Change, Ministry of Power, Ministry of Coal, New and Renewable Energy, MNRE, uh, Minister of Petroleum and Natural Gas, DAE, Department of Atomic Energy. So these are the some of the stakeholders in the energy policy determination. Okay. Now we will go for the bit of the technical things. So the routes for the energy production from the waste. So the solid waste and the biomass we will be covering, which will be focused upon. So this kind of solid waste and biomass can be converted to energy via thermochemical conversion, biological conversion, chemical conversion, and physical conversion. Under thermochemical conversion, we get the combustion, gasification, pyrolysis, liquefaction, those kind of processes. In biological conversion, it is carried out via the some processes based on the bacterias, based on the enzymes, those kind of biological sources, and which carry out the energy production via the, fermentation, anaerobic digestion, and these are the different like ultimate product which is used as an energy source are also shown here. Okay. So apart from that, the chemical conversion like the transesterification, hydrolysis, solvent extraction, those are the chemical processes. And a basic physical conversion. However, the physical conversion directly is not much helpful about the renewable fuel generation. So after the physical conversion, there is something usually nowadays which is being researched upon or has been emphasized on is to convert this kind of physically treated or physically converted biomass or the waste materials to further modify via this kind of different techniques, either thermochemical, either biological or chemical, or maybe nowadays if you see the photocatalytic or the electrocatalytic, these kind of processes are also being researched upon heavily. So they might be they come under I think the chemical conversion. So apart from the solvent extraction, transesterification, hydrolysis, the photochemical reactions, the electrochemical, electrocatalytic reactions, those are also very important nowadays for the energy production perspective. So the thermochemical versus biological conversion. If you want to compare this kind of two conversion routes, so basically a thermochemical conversion is carried out at a higher uh, temperature or the harsh conditions, usually require a high temperature and pressure conditions, and it's a very basically a much more conventional process, a much more conventional route. So its universality is very high. So it's effectively applied to almost any biomass feedstock. On the other hand, the biological route, it involves the use of microbes, enzymes, or different chemicals to utilize limited range of biomass. So, as they told that a high temperature and pressure conditions are usually required in the thermochemical conversion. So, it usually contains or usually results in a relatively higher rate of productivity. The biological process, on the other hand, due to the microbes, enzyme, or the bacteria, these kind of things are involved here. So the rate of production is usually low. So the rate of reaction, the rate constant, all those things are usually low. So it's a much slower process. However, a lot of things are actually in commercial scale also, such as ethanol or such as other maybe the furanic compounds. Those are actually commercially produced in a biological manner via a fermentation technique or some this kind of enzymatic technique uh, commercially because uh, this can be carried out at a much cost effective manner despite of having a lower rate. Okay. So similarly as the solid waste, the wastewater is also a good source of energy, and wastewater can be converted via the anaerobic digestion and further can be used as a biogas producing entity, and then this wastewater can be used in the microbial fuel cells and for further electricity generation. Okay. So there are also some challenges. There are also some regulations. There are also some other aspects which also we need to uh, stick together. So these all different technology options are not mature enough. Already uh, told that the thermochemical process is much more matured and much more developed from a long time. However, nowadays the commercially also the biological process is also done, but there are also this kind of photocatalytic, electrocatalytic, this kind of new age technologies, plasma technologies. These kind of new age technologies are day in day out they are growing. So they have been only proven in the maybe in the laboratory scale or maybe up to a pilot scale, but not in a very high commercial level. So those are the uh, other growing options which can be in the it can direct the change the way the waste to energy production technologies actually look or actually work out. Okay. And the regulation which we need to follow is the technology must meet all permitted environmental requirements established by the regulatory agencies. As already they are showed that there are different stakeholders which govern that the energy policies of our country, uh, and so the policies they make, these regulatory agencies, what they make. So our whatever developed technology, whether be it in pilot scale or laboratory demonstrated scale or some other technologies that particularly meet this kind of environmental requirement, and obviously it should be economically feasible as well. Yeah. So that was the to the second lecture. Okay. So from third to fifth lecture, what has been taught is basically the characterization of solid wastes, different physical characterization, chemical characterization. Among under the chemical characterizations, the proximate and ultimate analysis comes. Along with that, the fusion point of ash, lignocellulosic composition, the different leaching properties of the solid waste, and obviously the most important, the how much energy it actually contains, or how much energy it can actually produce when it would be used in a particular energy production technology. That heating value estimation is very important. And apart from that, the solid waste characterization, there are different characterization of the wastewater, such as the TDS, TSS, COD, BOD, the total suspended solid, total dissolved solid, total oxygen demand, chemical oxygen demand, biological oxygen demand. Those are the some of the things which are also being shown. Okay. So the physical properties which are important are uh, specific weight or density, particle size and size distribution, permeability or hydraulic conductivity, and moisture content. Those are some of the important physical properties. Among them, density is we all know that it's basically is the weight of the particular material per unit volume. So if you take a unit volume of material, how much weight it would be having. That is the uh, uh, density is defined as. Okay. So particle size and size distribution, particle size analysis can be done by different kinds of instruments, which are also shown here. And based on that, the particle size actually can be differential, it can be cumulative, and based on that, uh, it can be sieved or it can be segregated accordingly. Whether be it's we want our particles to be in the range of a certain within a certain diameter. For that, this kind of information are very important. Then the hydraulic conductivity. Hydraulic conductivity is a measure of the ability of porous media to conduct a liquid. Although testing of hydraulic conductivity is simple in theory, movement of water through a medium is very complex. Okay, so as is written here is basically the ability of a particular medium to conduct the liquid. So the different factors which are absolutely affecting the hydraulic conductivity are particle size, its degree of saturation, its properties, and its pore structure or its pore geometry. are important. Okay. However, this is a very important line that the MSW samples, the municipal solid waste samples, are actually very difficult to characterize based on only these kind of factors because the heterogeneity of municipal solid waste. Okay. So when we talk about the solid waste, that is the one of the major challenges which I think the solid waste management have. So the heterogeneity. So there are multiple varieties of the waste materials or the waste samples. So to characterize them based on a certain defined factor becomes a very challenging thing. Then the moisture content. So how it is determined? Moisture content is determined by using hot air oven where the material is heated at 105 degrees Celsius till the constant weight is achieved, and it's calculated in a simple formula. The loss in weight divided by weight of material taken. This will be the percentage moisture. Very simple. Similarly, the chemical properties of the solid waste can be determined by the proximate analysis, the ultimate analysis, the fusing point of ash, lignocellulosic composition. Uh, for the hazardous waste, it particularly the leaching properties, because again, because of their hazardous nature, we need to know if when you are carrying it, this particular waste, or when it is uh, uh, um, in contact with some other material, whether it would get leached or not. In some adverse conditions, it would get leached or not, because if, maybe some radioactive material is there, uranium, thorium. So those kind of radioactive material are very dangerous. Even in the ppm level or the ppb level, they are very dangerous, and they create some serious issue in the human body, right? So that is why this kind of leaching properties are important to um, understand and determine, and the energy content from the heating value. So proximate analysis gives us the details about the moisture content, volatile matter content, ash content, fixed carbon content via different ways of heating the material. Okay, and based on the uh, different municipal solid waste, their moisture, volatile, and this kind of composition is also absolutely very different. So if you see like the mixed food having a very high amount of moisture content, right? 70% moisture and only 3% of mixed carbon and 21% volatiles. On the contrary, the mixed plastics having a very less moisture and a majorly at the some the volatile matters. Okay, about maybe 95, 96%. So with this heterogeneity, is very becomes very challenging, and also obviously becomes very interesting also. Similarly, the CHNS analysis or the ultimate analysis gives us the carbon, hydrogen, nitrogen, and sulfur quantity of the waste material. Okay, and how it is actually calculated. It is basically calculated via the emission of the carbon dioxide, H2O, and nitrogen is usually an inert material, and SO2, so sulfur dioxide. So how much that particular gases are emitted based on that is uh, it's taken that, okay, that's like S plus O2 is SO2, right? So 1 mole of S would give us 1 mole of SO2. So if we get a certain amount of SO2 in the outlet, in the output, we get that this amount of sulfur is present here. Similarly with the CO2 and H2, all this, and N2 also, right? And also N2 uh, can become like only the nitrogen, or it can become the nitrous or nitric oxides also, N2 or NO2 also. So this, there are different chambers, there are different collecting traps, and absorbing traps where these particular different gases are selectively absorbed, and based on that they are quantified. Okay, so in the ultimate analysis what happens is high purity helium is used as carrier gas, and finally the gas mixture is brought to a defined pressure or volume state and is passed to a gas chromatographic system, GC. So the GC would give us the whether it's a nitrogen figure, CO2 and H2 and SO2 as I told. And via the calibration, you get the area under the curve of this particular gas, and we do the back calculation that as I already told that 1 mole of S would give us 1 mole of SO2. So by back calculation we get that okay, this amount of sulfur is present in our sample. Similarly with the other elements also. Okay. So other characterization technique is the fusing point of ash. So the fusing point of ash is the temperature at which the ash resulting from the burning of waste from a form a solid by fusion and agglomeration. So particular usually the waste material having a high fusing temperature, okay, about 1100 or 1200 degrees Celsius, okay. So it is actually the particularly the temperature of the ash which is getting formed after the conversion of the direct waste material. So we would be knowing that ash with what the operational range, operating temperature range of this particular ash as well. Okay, so uh, that is why these particular temperatures are important, and that is why the experimentally it can be determined by using furnace. Simply just taking the like different values of temperature and then checking that when that particular the ash is actually uh, forming a particular solid clinker by fusion and agglomeration. So usually ash is something like a powdery kind of material, but when it is in the furnace, it is either it's usually oxidized. When it's again oxidized at a very high temperature, then it usually undergoes some kind of agglomeration. Okay, and that particular temperature is called the ash fusion temperature. Okay. So now the another important thing is that the for lignocellulosic biomass, the analysis of the cellulose, hemicellulose, lignin, and extractives. Okay. So uh, for determination of extractives, it is already shown here that basically the dried sample is leached with benzene and ethanol mixture with a volume ratio of 2:1 at a particular temperature for 3 hours. After leaching, the residue is dried and in hot air oven to a constant weight, basically to remove the moisture. So ultimately, there would be a particular weight of the material, and then just see the how much amount of material is actually lost, and that is basically the extractive. Which means that the benzene and ethanol mixture is actually extracted that kind of material from your lignocellulosic sample. So that is called the amount of the extractive in the sample. Similarly, for determination of hemicellulose, uh, so after the extractives, so because otherwise these extractives, if you don't extract it, then it would be incorporated, or it would create some problems during these other materials calculations. So that is why the extractives are usually taken out earlier, and then the other hemicellulose, lignin, and cellulose determination. Okay, those are the details already like shown in the particular lecture. You should go through it. And also the leaching test is particularly for the hazardous material. So the leaching test is what it determines is the different heavy metals like arsenic, barium, cadmium. chromium, lead, mercury, selenium, silver, these kind of heavy metals, and some organic solvents like this carbon tetrachloride, pyridine, benzene, and all these things. Okay, and apart from that, some pesticides, those are also can be determined whether identified whether this particular material is present and it is getting leached or not. Okay, and some other reagents, and basically the extraction fluids quantity for uh, the waste to energy uh, conversion, and as a part of this particular characterization materials like the reagent water, the extraction fluids, the different types of extraction fluids, those are also very important. In line with this, the heating value determination is also a very important aspect, like heating value or the calorific value as we call it. It can be a higher heating value or it can be a lower heating value. Okay, so basically usually a common method is get the higher lower heating value and then add the heat of vaporization of the water. Okay, and just add them and then get the higher heating value. Okay, so how it is basically determined? It's usually determined using a bomb calorimeter. So it based on the particular principle that a known amount of solid fuel is burnt in a bomb. The generated heat is used to raise the temperature of certain volume of water kept in a bucket. Okay, the heat accepted by the water is equivalent to the heat released by the fuel. So very simple, like you place a particular sample in this particular bomb calorimeter and you ignite it. So it would get burned or combusted, and obviously there will be some heat generation. That generated heat would definitely increase the temperature of this particular water bucket in which this particular sample or the bomb is actually put. So the temperature increase is will from the temperature increase of the water will get the how much amount of the heat is generated from the material. Okay, see the detailed operating procedure is also shown here, like the sample of weight 1 to 1.5 gram is charged in bomb and it's pressurized with excess pure oxygen. It's submerged under a known volume of water before the charge is electrically ignited, as I told. Okay, and the weight reactant put inside the steel container is then ignited, and then the energy released by the combustion and heat flow released from this crosses the stainless steel wall and raises the temperature of the steel bomb. Its contents and the surrounding water jacket, that a particular temperature would be getting increased. The steel bomb temperature increased, its content temperature increased, and the water temperature is also increased. So that temperature change in the particular water then accurately measured and is correlated with the amount of the heat released. Okay, and then that kind of a heat of combustion calculation based on that. Okay, there is also a problem. We will be also discussing that particular sample problem. This. Okay, and how the way we get the particular gross calorific value, we use that particular uh, gross calorific value, and we also from that the using the net heat of combustion we can also uh, get the net calorific value. So there are some correlations are also provided here between the net heat of combustion and the percentage of the hydrogen and the particular the gross calorific value. Okay. And there are based on that there are different like correlations. for determination of this particular gross calorific value based on the fixed carbon and volatile matter, and also based on the CHNS analysis. So multiple authors, multiple scientists have given the different correlations. If you are asked in your examination, so might be asked in like this maybe like based on the Jenkins this thing, uh, determine the higher heating value of the particular material having this kind of composition. So like that. So I don't know whether they might give you the correlation or not. So you might also check this kind of correlation. Okay. And the final lecture contains the characterization of wastewater. So the characterization of wastewater involves the physical characterization, chemical, and the biological characterization. In the physical characterization, it contains the total solids, which has the total suspended solids, such as the turbidity, fixed suspended solids, volatile suspended solids, total dissolved solids, fixed amount that again the fixed or the volatile dissolved solid, and the simple the temperature, taste, odor, color, this kind of physical thing. The important thing are the chemical characteristics are the hardness of the water, your BOD and COD, biological oxygen demand and chemical oxygen demand. Nutrients, nitrogen and phosphorus, the amounts of the salts of the inorganic materials, mm, the salts of the inorganic constituents like calcium, magnesium, aluminum, chlorine, all these things, the carbonates and bicarbonates, and the heavy metals already discussed in the for the solid waste. Now similarly the in the wastewater also important. Now also the total organic carbon TOC and the dissolved oxygen. Okay, so there are different analytical methods. Can check there for the total suspended solid turbidity meter. That's for the color. There is spectrophotometer for odor, threshold odor number, like that, etc. etc. Okay. So for the trace metal, the AAS, the ICP-MS, so all these materials are used. So AAS and ICP-MS, these are also very important characterization, and I don't know whether they have not detailed covered in this particular, but you should also check their basically the application and the principle also. Okay. ICP-MS stands for the inductively coupled plasma mass spectrometry, and AAS is the atomic absorption spectroscopy. So these are usually used for the metal determination or the trace metal determination up to the ppm or ppb level even. Okay. So for solid material as well as the liquid material, those are used. So apart from that, the uh, dissolved oxygen measurement is also carried out via usually via Winkler's method, where an excess of manganese salt, iodide salt, and hydroxide ions are added to a water sample. So the dissolved oxygen, what it does is it converts the manganese salt, like the manganese ions Mn2 plus, to a MnO2. So from that MnO2, this particular manganese containing precipitate is dissolved back to the solution where it gets some precipitate and some acid conditions. What it does is that MnO2 get again dissolved, and then particular that particular MnO2 is converted into the Mn2 plus uh, salt in the dissolved state, right? So that iodide ion, and via that what happens is the iodide ion, it gets converted into the elemental iodine, and by that the dissolved oxygen is usually calculated. Okay, so like that only. Okay, apart from that, the dissolved oxygen, apart from the ring class method, the important thing is that the membrane electrode method. So that by membrane electrode method, what happens is that in a typical dissolved oxygen sensor, there are the two electrodes, a anode and the cathode. The cathode is usually made up of a gold, the anode is made up of a silver. Okay, so they are usually immersed in a particular electrolyte solution, and they are separated from the sample to be measured by a gas permeable membrane. So there is certain uh, permeation between this particular within the electrolyte within the cathode and anode, and the certain chemical reaction which are occurred, and the gold cathode, there is the oxygen plus 2h2 plus 4 electron gives us the hydroxyl ion, and the silver anode, there is the AgCl, silver chloride formation. Okay, and based on that, we get that amount of the uh, resulting like current flow. Obviously, there's a migration of the ions towards cathode and anode from the electrolyte, and the what amount of current is flowed, that is actually measured, and that resulting current flow is usually considered as a directly proportional to the dissolved oxygen content on the stream. And how it does proportion is because of this kind of reactions in the gold cathode and the complementary reaction and the silver anode, and by that back calculation of the current flow, and by the current flow and it's proportional to the dissolved oxygen content, we get the uh, DO, dissolved oxygen. Similarly, the BOD and CODs, these are also you should check. I'm not going to much detail of the biological oxygen demand and the chemical oxygen demand, and also the total organic carbon test also. Okay, those are as I told earlier, that the atomic absorption spectrophotometer is also very important. See, they have shown here with the working principle of the atomic absorption spectrophotometer, which is usually used for the metal determination or the metal content determination at a very low quantity as well. Okay, and apart from that, the chemical kind of properties, some bacteriological or biological measurements are also done, like based on the membrane filter technique, and some other like the total solid and total volatile solids also. Those kind of methodologies you should also check once. Okay, so after that we'll check some of the sample questions. Okay, so the first question is, which of the following is not a quality parameter of solid wastes? Elemental composition, heating value, bulk density, BOD and COD. So you can answer via the chat box, uh, and after each question we'll have a brief pause, about 2 minutes, and then again we'll discuss. So the correct answer is the B, BOD and COD. BOD and COD is basically quality parameter of the wastewater, not of the solid waste. So the biological and chemical oxygen demands. Biological and chemical oxygen demand are the properties of the wastewater. It's not a parameter of solid waste. So somebody else also told that bulk density, not bulk density is a very important parameter of the solid waste along with the heating value and elemental composition. Okay. Based on the source of occurrence of wastes, solid waste can be classified as municipal solid waste, industrial solid waste, agricultural waste, all of the above. So yeah, the all of the above is the correct answer. So the classification of solid waste are actually made based on source, based on its biodegradability, based on its combustibility, compostability, usability. Okay. So based on source, basically municipal solid waste, industrial solid waste, agricultural waste, these are the basic classifications. Apart from that, it can be biodegradable, non-biodegradable, combustible, non-combustible, compostable, non-compostable, and also it might be inert in nature, it might be in recyclable or organic in nature. So these are the basic uh, classifications. Which of the following is not a thermochemical conversion route for energy production from wastes? Combustion, gasification, briquetting of biomass, or pyrolysis. Which of the following is not a thermochemical conversion route for energy production from wastes? Combustion, gasification, briquetting of biomass, or pyrolysis. So yes, the correct answer is briquetting of biomass. See, so it's basically a physical conversion process, not a thermochemical conversion, as I already discussed. So you have to match these things together, find the most suitable option to match the following biomass conversion routes with their appropriate technologies. The biomass conversion routes with the technologies you have to match. So yeah, the first option is the correct one. So readily can be seen that thermochemical conversion is the pyrolysis is basically a thermochemical conversion. Anaerobic digestion is a biological conversion. The solvent extraction is a chemical conversion, and the briquetting is a physical conversion. Okay, so it's 1R, 2Q, 3, what is it, S, and 4P. It's correct. Okay, so the particle size of the solid waste can be analyzed by sieve analysis, Trommel's particle size analyzer, or all of the above. So yeah, the correct answer is all of the above. So sieve analysis, Trommel's, and particle size analyzer all can be used to measure the particle size and the particle size distribution of the solid waste. Okay. So in proximate analysis, the moisture percentage is measured by drying the sample at the temperature for what time. The temperature and the time you have to tell. So the correct answer is 105 degrees Celsius for 24 hours. Okay, so the moisture content is usually captured via the loss of weight in sample due to the it's drying at 105 degrees Celsius for 24 hours in the proximity analysis. So lower heating value is determined by subtracting the heat of vaporization of the water from higher heating value, latent heat, net calorific value, or none of the above. Yeah, so the correct answer is A, higher heating value. So basically, higher heating value is summation of lower heating value and the heat of vaporization of the water for the latent heat. Okay, and to determine that particular heating value, I've already showed that the bomb calorimeter is actually used, and basically the amount of temperature of the water that is increased, uh, that is correlated with the heating value of the sample. Generally, what solution with normality of 0.25 normal is used to determine the COD in wastewater? Sodium chloride, sodium hydroxide, potassium dichromate, none of the above. So the correct answer is the potassium dichromate. So for the COD measurement, you have to take the sample plus the excess of the potassium dichromate and sulfuric acid and then heat it for 2 hours under total reflux condition. And usually the 0.25 normal solution of potassium dichromate is used for the chemical oxygen demand determination. Okay, so the during the digestion of this particular chemically oxidizable material, stoichiometrically equivalent amount of dichromate is actually get reduced, and the amount of Cr3 plus is determined after the complete oxidation, and that is used as the indirect measure of the organic component of the water sample. Okay, so the Cr3 plus, then see that amount of the Cr3 plus is get, so it is used as the indirect measure of the chemical oxygen demand content of this particular wastewater. The atomic absorption spectrophotometer works on the best principle of inverse square law, Lambert-Beard law, Beer's law, or none of the above. So the correct answer is Lambert-Beard law. So the atomic absorption spectrophotometer basically works on basis of this particular Beer-Lambert's law. Okay, which acts on the absorbance is directly proportional to the wavelength, the determinant of the basically the path length of the particular ray, the light source. Okay, and the analyte concentration, and which is the proportionality constant is epsilon, which is termed as the absorptivity coefficient. Okay, and so this is the last question of the day. Uh, a solid waste with 1% sulfur is combusted in the bomb calorimeter. The temperature of the bucket water increases from 25 to 28 degrees Celsius. The water equivalent of the calorimeter is 2402 calorie per degree Celsius. 1 gram sample is used for the test, and the per 45C10 wire is used for the ignition. Out of the 10 centimeter wire, 2.6 centimeters is unused to titrate the calorimeter. This much of sodium carbonate is required. So gross heating value we have to calculate. So you have to basically use this kind of formula, the gross heating value, which calls as the multiplication of the T and W minus E1 minus E2 minus E3. So for the, I think I'll go to the yeah. So this is the basically gross heat of combustion value, okay, which the H is T multiplied by W minus E1 minus E2 minus E3 divided by M, okay. So W is basically the energy equivalent of the calorimeter, okay, and E1, E2, E3, these are the correction factors. So E1 is basically equals to C1, C1, E2 is basically 13.7 into C2, and E3 is basically based on the where is used, it's 2.3 into C3 or 2.7 into C3, or it can also be 0. And M is the amount of the material used, okay, the mass of the sample. What are the C1, C2, C3? C1 is the millimeter of the standard alkali solution used in the acid titration. C2 is the percentage of sulfur in the sample, and C3 is a centimeter of fused wire. Okay. So now we put the values. So basically W water equivalent. So water equivalent is given 2402. Okay. M is 1 gram. It's there is given that 1 gram of sample. Okay. The amount of now put the T value. What is T? T is basically the difference of the temperature. So the temperature of the water would increases from 25 to 28, means 3 degrees. So T will be 3 degrees. Okay, so it's 3. W is 2402. Now E1. E1, as I told, it's equivalent to the C1 value. Yeah. So E1 is basically equivalent to the C1 value. What is the C1? So C1 is given as 24.2 ml. So calorimeter, this sodium carbonate solution volume. So it's C1 24.2. Now C2. Now E2 is what will be the E2? For E2 is given that par 45 C10 wire is used. Okay. So what is the par 45 C10 wire? What it will be 2.3 into C3, right? So for E3, right? So 2.3 into 7.4 you have to use. Okay, the C3 is given that how much wire is basically used. So 10 minus 2.6 is 7.4. So 2.3 into 7.4, it will be 1783. And similarly, the E2 will be 13.7 into E2. Okay, that is the E2. 13.7 into C2 into M. Okay, M is 1, C2 is given, C2 is also 1. So 13.7 into 1 into 1. Okay. So it's given, right? 1 gram of sample is used and like that. Okay. Now put all the values and you'll get the gross calorific value. It's 7150 calorie per gram. That's it. So that's all from my side today. So wish you the best and we'll meet you again the next week. Thank you.
Sir, how many class in a week?
So there are two, I think two sessions are there. One will be taken by me on this day at this time, and there is another one, I think. You will have to just check out the notification of them. So basically two sessions are there, I think. Yeah. But I will be taking one session.